Hello, Sean. We cannot hear you right now. If you could please go to the top left-hand corner and hit the microphone so that it is green so that we can hear you. As of now, I cannot hear anything from your side. Sean, are you there?
Okay, we'll start now then. Can you hear us now?
Okay, sounds good. Yes, I can hear you guys now. You guys may begin now. Sorry for the interruption. And you are...
Okay, so we'll start now then, okay? Okay, so
okay, you are good to go.
Good morning, everybody. Okay. So good morning, everybody. Sorry for the brief delay. My name is Thomas Mueller, and I'm the Director of Applications for the AFM business at Bruker. We'd like to welcome you to this installment of our Bruker AFM webinar series. This presentation today is titled Silicon Nanowire Hybrid Metrology for the 7-nanometer node. It's presented by Sean Hand. And before I introduce Sean, I'd like to make a few quick logistical comments. We should be back on our title slide now. Sorry for the brief delay we had. So first, we encourage your participation during the webinar. If you have a question, please type it into the questions dialog box on your screen. We will accumulate these questions to the presentation, group them together, and then answer them at the end of the prepared remarks. Quite often, we have more questions than we can answer in the session, and in those cases, we'll be sure to follow up with answers via email afterwards. Also, if you would like to review the presentation afterwards or pass it on to a colleague, the webinar will be posted online within a week in the webinar section of the Bruker webpage. As a follow-up to this presentation, you will also be receiving an email with this link. Finally, when you exit the webinar software, you will be asked to take a brief survey. We'd very much appreciate it if you would take the time to complete this, as it helps us pick the topics that are most important to you and to generally make the series better. So let's get started, and let me introduce our presenter. Sean Hand is a Senior Staff Application Scientist here at Bruker Nanosurfaces. Sean has been with Bruker for 14 years and has focused primarily on applications of the automated AFM in semiconductor manufacturing. Sean holds a BS and MS in physics from the University of Vermont. So let me turn it over now to Sean to begin his presentation titled Silicon Nanowire Hybrid Metrology for the 7-nanometer node.
Good morning, Thomas, and good morning, everyone. Thank you very much for that introduction. My name is Sean Hand, and I would like to welcome you to this morning's webinar, Silicon Nanowire Hybrid Metrology for the 7-nanometer node. In this webinar, we will cover the concepts of hybrid metrology and its application to advanced node semiconductor devices. Here's an outline of this morning's webinar. We will begin by discussing the motivation behind the hybrid metrology concept and technique. We will then move on to review the 3D AFM platform that was used for this work and the scan mode, PeakForce Tapping, in which the data was acquired. Next, we will discuss recent advances in design-based metrology, or DBM, for the Insight 3D AFM platform and its application to hybrid metrology. At this point, we will go into a case study of hybrid metrology for the gate-all-around silicon nanowire. First, we will review just what the gate-all-around silicon nanowires are and why they are of interest for advanced node semiconductor devices. We'll review some previous work that was done with an SEM to characterize the morphology of these silicon nanowires, and then follow up with the hybrid metrology work that was done to more fully characterize these structures using the AFM. So as semiconductor devices continue to shrink, it has become increasingly evident that no single metrology technique is capable of providing all of the information needed for device development and process control. This challenge increases for advanced node devices such as non-planar FETs and novel device structures. In recent years, the concept of hybrid metrology has been brought forth as a solution to this problem. Hybrid metrology utilizes the strengths of two or more metrology techniques in concert with each other to provide measurements of value. This webinar presents the role of atomic force microscopy and hybrid metrology for current and future node semiconductor devices. The gate-all-around silicon nanowire is one such structure that is under investigation for introduction at the 7-nanometer node. A recent case study in which hybrid metrology between a CD-SEM and the AFM was used to investigate the buckling characteristics of 7-nanometer silicon nanowires. The AFM used for this study is Bruker's fully automated Insight 3D AFM. The Insight 3D AFM provides proven production-based depth metrology extendable to the 10-nanometer node. Along with depth metrology, the Insight 3D AFM supports CD mode for true 3D device morphology characterization, ideal for today's non-planar FET and OPC development. The 3D AFM also provides TEM-level profile measurements in a fast and non-destructive fashion, permitting pre- and post-process profile evaluation. Lastly, and most closely related to today's topic of hybrid metrology, the Insight 3D AFM provides unparalleled reference metrology for fleet matching, process monitoring, and OPC model development and verification. The Insight 3D AFM supports 4 AFM modes in a fully automated platform. Tapping mode for surface and film roughness, PeakForce Tapping for material characterization and extended depth capability, Deep Trench or DT mode for depth metrology, and CD mode for critical dimension metrology. In this webinar, this work will focus primarily on PeakForce Tapping. Webinars focused on the other modes and techniques for the Insight AFM may be found on the Bruker website. So what is PeakForce Tapping? As the name implies, the probe is in fact tapping the sample surface, but is doing so at a frequency far below the resonant frequency of the cantilever. With each tap, as the probe comes into contact with the surface, the cantilever is bent or deflected upwards, as we see in the diagram at left in Figure C. The amount by which the cantilever is deflected is related to the amount of force on which the cantilever is pushing into the sample surface. As its name implies, this force plays a key role in this mode of the feedback in this mode of operation. When the amount of force being applied to the sample by the probe is equal to a user-defined set point, or the peak force, the cantilever is withdrawn. This method provides unparalleled force control and resolution and has enabled applications such as the silicon nanowires, about which we will speak shortly, that are not possible with contact or resonant-based feedback methods. So what is hybrid metrology? Quite simply, hybrid metrology is a utilization of data from multiple complementary metrology tool sets to generate measurements of interest. The concept of hybrid metrology usually utilizes 2 or more complementary techniques to obtain a measurement of a sample of interest. In general, there are 2 ways to go about this task. The first is a more statistical approach in which a large set of measurements is made on a sample by both tools, and these results are hybridized to generate a result. Examples of this type of hybrid metrology would be an AFM with an optical CD tool, in which many measurements are made over several OCD grading targets, but measuring the exact same feature within the target is not critical. In the second case, as shown at right, all tools that should be used in the hybridization measurement must measure the same feature and exactly the same feature. In this example at right, a process-stressed artifact gate analog is measured by both the cross-section TEM and the CD-AFM. As is clear from this example, both metrology systems measure the exact same feature. That both metrology systems measure the exact same feature is critical to the success of the hybrid measurement. A key example of this type of hybrid metrology is the use of the CD-AFM and the CD-SEM for optical proximity or OPC development. So as mentioned earlier, the concept of hybrid metrology uses 2 or more complementary techniques to obtain a measurement of a sample of interest. And in the last foil, we clearly demonstrated the importance of measuring the same feature for certain types of hybrid metrology, such as OPC. In order to enable this type of hybrid metrology for inline applications, both systems must be able to utilize the same critical information about the sample, such as flash field size, global alignment, mark locations, and most importantly, be able to navigate to the measurement site of interest without any operator or engineer intervention. To this end, design-based metrology, or DBM, is the clearest path forward. In design-based metrology, all of the information required to locate and execute the measurements comes from the design or CAD data of the wafer, chips, and targets. To enable the Insight 3D AFM for design-based metrology, 4 new capabilities have been deployed: AFM global alignment, multi-point registration, XML recipe generation, and CAD-based SPM Zoom. So first we're going to talk about the multi-point registration. So due to process variations, the design coordinates will never exactly match up to those printed on the wafer, especially when one is looking at the nanoscale. To first order, the translation and rotation are removed by an origin and a D-skew alignment. This, however, does not take out the patterns, non-orthogonality, and scale. Multi-point alignment has been adopted to dynamically correct for both of these issues. So as many global alignment targets as desired may be used, in general, more than 5 does not significantly improve the image placement accuracy. Traditionally, the automated AFM relied on optical pattern recognition of the global alignment targets alone. With a pixel size on the order of a micron, this strongly contributed to the lower limit of how accurately a target of interest could be centered in a data scan based on design coordinates. Using the AFM brings this resolution far below the micron and at the same time removes any residual offset between the optical navigation and pattern recognition system and the AFM probe. The run flow is shown here at left. The optical pattern recognition is still employed for a coarse alignment post-wafer load, but after each optical pattern recognition is followed by an AFM fine alignment step pattern recognition. Access to the chip design data and the CAD Clips is all great for design-based metrology, but all this data, and there can be a lot of it, must be compiled into a recipe that can be run on the AFM. To that end, an XML-based recipe format of recipe generation has been developed. All of the design data, references to CAD Clips, and scan parameter information required to generate a recipe for the AFM is contained within this XML file. This XML file is easily edited and modified for rapid recipe development and ease of use. All measurement outputs, of course, have vids for host upload, but may now also be reported in an XML format for consumption by other metrology systems for hybrid metrology. And lastly, as you may know, the SPM Zoom is the last fine positional adjustment performed by the Insight 3D AFM before data acquisition. This is the step that ensures that the feature of interest is located within a few nanometers of the image center. Traditionally, to teach models to be used for SPM Zoom, a representative sample was required from which to acquire an example image on which to teach the model. This is counter to the design-based metrology approach in which no sample is available at the time of recipe teach. To enable SPM Zoom for design-based metrology, the SPM Zoom step is performed on an imported CAD clip of the region of interest. Nanoscope supports GDS2, OASIS, and TIFF for CAD-based SPM Zoom model teaching. So with these new capabilities for design-based metrology, it is time to deploy them in a hybrid metrology scheme. In the case study that I will outline in the remainder of this webinar, a hybrid metrology approach was used between the CD-AFM and the CD-SEM. Design data and the XML recipes that were generated and sent to both the CD-AFM and the CD-SEM. This data was then consumed by each tool and a recipe was generated. The output data of these measurements could then be hybridized into actionable results for the fab. As a first step, a target wafer with a uniquely identifying defect was used. Presented here are some of the initial results from the CD-AFM, CD-SEM hybridization work. At left is the CAD clip used for the SPM Zoom, with the SPM Zoom model target outlined in blue and the data scan location outlined in orange. The center of the CAD clip is indicated by the green dashed cross. At center is the 3D rendering of the AFM image with the target of interest, and at right is the corresponding CD-SEM image clearly showing the same target of interest. This example also clearly shows the benefit of the hybrid metrology approach. The defect in the target is clearly visible in both the CD-SEM and the CD-AFM image. However, the 3D AFM morphology is not clear in the CD-SEM image. Is it below the surface of the lines, above it, or perhaps it is flush? The AFM image clearly shows that the defect in this case is significantly taller than the lines. The combination of this data for both the CD-AFM and the CD-SEM provides far more actionable information than either system alone. So, as a quick acknowledgement, the results that will be presented in the following slides were generated out of collaboration with IBM and Applied Materials. A portion of these results that will be presented here were presented at SPIE's Advanced Lithography Conference this past February. So silicon nanowires and silicon nanowire buckling. Silicon nanowires are a promising option for advanced node gate devices. However, they do suffer from a critical process issue in that they do tend to buckle. This buckling can negatively impact the device performance, and so it is critical to understand the characteristics of this buckling and how it occurs. In the initial work, the CD-SEM was used to characterize the silicon nanowires, and this buckling was observed. It was unclear if this buckling was being induced by the CD-SEM or was an effect of the measurement by the CD-SEM. From the SEM measurements, it was clear that the buckling of the horizontal or x-axis was uniformly distributed to both the left and the right of center. The buckling in the z direction, though, had a clear bias towards buckling towards the wafer. No silicon nanowires were observed to buckle away from the wafer. The AFM was then used to characterize the same silicon nanowires measured by the SEM. Feature co-location was performed by an XML recipe exchange between the Insight 3D AFM and the CD-SEM. It was quickly determined, however, that the resonant-based feedback of CD mode would not provide sufficient and immediate force control in order to be able to measure the delicate silicon nanowires without disturbing them. In order to be able to image the silicon nanowires, the precision force control of PeakForce Tapping was required. Measurements were performed using a Bruker scan assist air probe. What we're looking at here is an example image of the same target as measured by both the SEM and the AFM. Both the SEM and the AFM show the same buckling characteristics. In this case, both the CD-SEM and the AFM, there are wires that buckle to the left, and there are wires that buckle to the right of the wire center line. In all targets, the morphology of the buckling match between the CD-SEM and the CD-AFM, indicating that the silicon nanowire buckling is not a measurement artifact of the SEM or of the AFM. Here we see the AFM image rendered for hybrid metrology comparison to the SEM. An overlay of the SEM data for this target clearly indicates the same buckling morphology. Inset is a comparison of CD measurements for the AFM and the CD-SEM. The scan assist air probe was not qualified against a standard such as the nano-CD prior to these measurements, and this large intercept offset of about 9.5 nanometers may be reasonably associated with the probe's width at the height at which the silicon nanowires were measured. Also, like the SEM, the AFM measured all buckling of the silicon nanowires in the Z direction to be towards the wafer surface. No wires were observed to buckle away from the wafer surface. A comparison of the Z buckling characteristics of the silicon nanowires as measured by the AFM and the CD-SEM is shown here. Each curve represents the height of the wire above the wafer surface along the length of the wire from source to drain. The relative offsets of the curves in the AFM plot indicate the small variations in the anchor points of the silicon nanowires to the source and drain. Here we present Mandel fits for each of the silicon nanowires in the previous image for TMU comparison for the height measurements for each of the 5 wires. The loop that you observe in the appearance of the plots is representative of the wire sagging between the anchor points at which the same Z positions for a given wire. And lastly, here we present the TMU measurements for comparison of the CD-SEM to the CD-AFM. I'm sorry, to the AFM. You can see here that in large part the AFM provides very good TMU. And so, in conclusion, as semiconductor devices move more towards smaller and more complex topographies to meet the challenges of advanced nodes, hybrid metrology has emerged as a necessity to meet the metrology requirements for device development and production. Design-based metrology, or DBM, enables hybrid metrology through the seamless exchange of critical information between metrology systems. The Insight 3D AFM is design-based or DBM capable through the recent advances of multipoint AFM registration and XML and CAD-based recipe generation. As a case study, recent collaborative work with Applied Materials and IBM has demonstrated successful hybrid metrology for gate-all-around silicon nanowires using design-based recipes and results exchanged between the 3D AFM and the CD-SEM. I'd like to thank you very much for your time this morning. If you have any further questions or would like more information regarding this work, please feel free to contact me directly at the email address presented here or your local Bruker representative. Thank you very much.
Okay, thank you. Thanks, Sean, for the presentation, and thank you, everybody, for attending. Let me have a brief look at the questions submitted so far. We have time certainly for a question or two, and should you have more questions afterwards, don't hesitate to follow up with us, with Sean, or as he said, with the local representative on the content. So let me have a quick look here at the questions box. I see several questions in a sense about upgrading here. One is really, is this available as an upgrade to my current tool fleet?
There are software portions of the, yes, the software portions are upgradable to a current tool fleet. So this would include the multipoint registration, the AFM global alignment, the XML-based recipe generation, and the CAD-based SPM Zoom. PeakForce Tapping is not a software upgrade. That's actually a hardware upgrade.
Okay, very good. Thank you, Sean. And there was a different question here. What would be needed to enable PeakForce Tapping on an Insight 3D AFM?
So again, that's a hardware upgrade, and so that's something we would have to work through with your local sales representative on how to make that happen.
Okay, very good. Thank you. So that's it for now. Actually, we're running out of time on this webinar. Let me thank all attendees again for joining us. Please do take the time to take the survey, and we hope to see you again for our next webinar. Thank you. Bye-bye.